All right, hello everyone. So my name is Niels Lucas and I'll be presenting, like was already introduced, for Eric and Florian, who made a paper on private collaborative data cleaning via Non-Equi PSI. Unfortunately, both authors couldn't come, so I'll try to represent their paper as well as possible. Okay, so first, what is data cleaning and why is it even necessary? So data cleaning is the act where I, as an SOC, so as a security operating center, I have some data and I have labels for that data. So in this case, I have some IP addresses and I have a label for them. In this case, is the application connected via that IP? Is that a malware or is it not a malware? Now, what I want to build as an SOC is a classification system, for example, and building a classification system can be done via two ways. So way number one is you increase the amount of data that you have, and way number two is you increase the quality of the data that you have. And data cleaning is a way to improve the quality of your data. Now, there's other security operating centers, so in this case SOC2, who has similar data, but and now I would like to join my data with their data in order to assess whether we labeled similar IPs with the same label. And if we could do that, then we could effectively clean our data out and find mismatches between both data sets. The problem, of course, is that these SOCs, they don't trust each other, so they cannot compute this mismatch in the clear. So we already know, I think this is likely a problem that is well known here, is the problem of private set intersection, where we compute the intersection without revealing the inputs to each party. And this is a variation on that, only that we compute the mismatches. So that's going to be the goal of this paper. So there are some technical challenges here. So first, the paper presents a strawman protocol for a circuit PSI implementation. So in this case, what the output would be in the ideal case is Alice and Bob, they have this key value store. And now an ideal functionality would just output the indices of the mismatch, meaning that the keys are matching, but the values are not matching. And in circuit PSI, computing the circuit PSI is cheap. So what we would get out of that, there's existing protocols for it, is that if the keys are equal, then we get a share of the comparison and a share of the value. But then in order to compute the expensive part, which is the mismatch, we would have to engage in a two-party computation protocol. And in this case, we would have to compute the statement whether the keys match and the values don't match. And that is very expensive because it has high bandwidth requirements. So the question is whether we can do better. And this is essentially where the contribution of this paper comes in. So there's a very, very simple trick. And that is we decompose the values into bit representations. And then we can construct a sequence out of their prefixes. So we now have a value such as 101 for VI. And now we build the set of all of its prefixes of a given length, which is going to be L elements, essentially, if we have L bits. And we do that between both parties. And then there's an interesting observation is that we know that there's going to be a mismatch between these two values if we can, if there's at least one prefix that differs. And if Bob now flips the last bit of their prefix generation of their set, like of every prefix, if they flip the last bit from that, then what we would have to do is we would just have to compute a private set intersection cardinality on the two prefix sets in order to determine whether or not we have a match or we don't have a match. So what we effectively did here is we turned the problem of finding a non-match into the problem of finding a match, for which we have efficient methods of doing so. Now there's two remaining challenges, and that is so far we've only compared the values with each other, but not the keys. And also we have to, of course, avoid the squared complexity of comparing each element with each other element. So the paper in total presents 3 protocols, and I'm only going to present 2 out of these 3 protocols, and the last one I would refer to the paper for this. So the first, those 2 protocols, they're variations of each other. So this is a Diffie-Hellman protocol, base protocol. So in this case, what Alice would do is they would compute the PRF of the key, concatenate it with each of the prefixes. So they would send L PRFs, essentially, over to Bob. Bob would then apply a random permutation in order to hide which bits would be leaking, and then send that back to Alice. And then Bob would do the same thing for all of their inputs, where they only flip, as I mentioned earlier, they flip the last bit of the prefix generation. And as a result, Alice would then just have to count the number of matches in the set of PRFs that they have. And if they see that there's one match, then they would know that there is a mismatch. And this is an element that needs to be cleaned, essentially. The problem with this protocol is that it resorts to a lot of public key operations, which are very expensive computationally. So specifically, it's going to scale in the number of inputs linearly, in the number of inputs, and in the number of bits. So the question is, how can we alleviate that? And so there are actually OPRFs that are very efficient. So this is supposed to be animated. Those are not my slides. So the slides might look a little bit weird, probably. But essentially, we have 2 efficient implementations for these OPRFs, which are the KKRT and VOLI OPRFs. And so they have the number of public key operations that they are doing is linear in the security parameter. So essentially, there's one problem that we didn't encounter before. It is that now we have a vectorized representation of all these inputs. So we cannot shuffle anymore, which was necessary earlier. So here, one trick that is well known is to apply cuckoo hashing. And in this case, stashless cuckoo hashing, which enforces the same ordering between Alice and Bob. And then what happens is that Alice and Bob, they send the PRFs of each, like in the previous step, they send the PRFs of their keys with the prefixes over to each other. And they use 3 hashing functions in this stashless cuckoo hashing. And essentially, they construct this table where they mask elements with a random token. So that's the mask1 token. And with the PRF they obtain from Bob, they send that over to the other party. And now the other party can actually unpeel and extract or get the mask out, XOR their input, send that back. And all Alice has to do is that if she finds a mask, then she knows that this was a mismatch. And this is a more efficient, a computationally more efficient protocol. So for the evaluation, so the paper itself has a lot of, an entire page where they go through a lot of scenarios, and they find that in the very high bandwidth regions, so we're talking 1 gigabit per second, the strawman approach, like the naive approach that I gave very early, actually works really well. However, once you limit the bandwidth of the protocol, it becomes much worse, the strawman construction. And then they ablate over the amount of labels that you can have about on the bandwidth and so forth. And they find that their approach, depending on the setting, outperforms the strawman approach in between 10 to 30 times. And they go through different label settings and motivate those why they're relevant in practice. Yeah, but the most important conclusion, I suppose, or so I was told, is that the private data cleaning is an important problem that hasn't been looked at so far, and that this is the first approach at solving it, and that they found very efficient and practically relevant methods of doing so. And yeah, So I should also refer to the paper for the second protocol, which has some leakage, namely the size of the intersection between all elements, which can be hidden with DP, with differential privacy. Yeah, and that's essentially it. Thank you.
All right, do we have any questions? Come to the microphone in the center.
Hi, very nice work. I was wondering, can't you just run 2 PSI, one for the keywords and one for the values? That will give you the differences, because the keywords will tell you if they are matched, and the values will say if they are not matched. And then all you have to say is, okay, where my keys are matched, and then where my keywords are not, values are not matched. That should do the same thing. Or is it like heavy in computation?
I don't think it's quite as easy. So you're saying you have 2 PSI protocols on the keys and the values?
Yeah.
But then you would still have to compute the mismatches, right?
So the PSI on the values will be there to detect the mismatches, because it will tell you where the matches are. So all you have to do, okay, first PSI will give you all the matches of the keyword, right? Mm-hmm. And the second PSI will give you all the matches of the values. And all you have to say is where my keyword matches and my value doesn't match.
But you don't know how they match together, right?
One of the party knows their keywords and values, right? Each party knows their keywords and values. Can't they just, they get the result of the PSI? I'm talking about the one-sided PSI where one party gets the result.
Yeah, but even then you would still have to do that for the key and the value, and you would still need to find out all the mismatches, if I understand correctly, right?
Yeah, so let's say there was only one keyword and one value, okay? Mm-hmm. You run a PSI for it. Now you get the keyword, result of the PSI for the keyword, which says it's 0, that it's a match. Mm-hmm. And you get the result of the value, which says 1, that it's a mismatch.
Oh, okay.
Now you know it's a mismatch.
Okay, but you still would have to, you only want to reveal the mismatches, right? So nothing else.
Oh, it reveals the match. Okay, so yes. It's more leakage.
Exactly, yes.
Okay, makes sense. Okay, thank you.
Yes. Yeah, thanks for the question.
All right, I guess I had a quick question. So they mentioned this differentially private protocol. Is that allowing for a more efficient construction?
Yeah. Oh yeah, that's a great question. So in the paper, they have a whole, I think, page even dedicated to that. So in certain circumstances, yes, it's more efficient and substantially more efficient. And however, it's not always more efficient. But one of the nice aspects is that the communication is independent of the length of the label size in that protocol. So, so if this additional leakage is allowed, with especially with masking it through differential privacy, then it can have, for a lot of evaluated setups, it can have a lot of usage.
All right, let's thank our speaker.